Hi, have you ever heard the term power factor and wondered what it really means? If you're familiar with the basics of electricity, stick around as we explore how power factor impacts electrical circuits. We'll break it down by looking at active, reactive, and apparent power, and how adding inductive or capacitive loads shifts current and voltage, influencing the power factor. Let's start with something simple, DC circuits. With DC, the voltage and current remain steady, as shown in this graph of straight lines. There is no change in direction or magnitude. It's straightforward and predictable. Now let's add a power line, this green line, and it also remains steady. Power is simply voltage times current, so as long as current and voltage are steady, power is going to be steady and constant. And here's a simple DC circuit with a battery and a switch and a light bulb. Current flows steadily, as represented by the yellow dots powering the light bulb. There's no oscillation, no phase shifts, just pure steady energy flow. Now let's look at alternating current, or AC. In an AC system, voltage and current oscillate back and forth in a sinusoidal pattern. On this graph, the red wave represents voltage and the yellow wave represents current. Notice how they align perfectly. When voltage is positive, current is positive, and when voltage is negative, current is negative. If we multiply these together, the resulting power is always positive. That's because voltage and current are in sync. All right, now let's look at an AC circuit. In this case, the circuit has a purely resistive load, like a light bulb, meaning the voltage and current are always in phase. This gives us a power factor of 1, which is the most efficient. There's no energy losses, except for a little bit due to resistive losses in the wires, but we're going to ignore that for this discussion. Now let's complicate things a little bit by adding two components that behave differently from resistors. These are inductors and capacitors. Inductors resist changes in current by storing energy in a magnetic field. When the current increases, the inductor opposes it, causing the current to lag behind the voltage. This is often remembered with the memory aid ELI. In an inductive circuit, voltage leads current, or current lags voltage. And now capacitors, on the other hand, resist changes in voltage by storing energy in an electric field. As the capacitor charges and discharges, it causes the voltage to lag behind the current. And this is remembered with the memory aid ICE. In a capacitive circuit, current leads voltage. Some people like to remember this with the mnemonic Eli the Iceman. Okay, to summarize, inductors resist change in current, leading to a current lag, while capacitors resist changes in voltage, leading to a voltage lag. Both of these components create a phase shift between current and voltage, which affects the power factor. Let's adjust this graph a little bit. This time, let's add power onto the graph. The red graph shows the power, which is calculated by multiplying voltage times current. Here you can see that power is always positive. But what happens when the current and voltage become out of phase? Let's put this graph in motion and show different amounts of phase shift, and we'll see what happens with power. Remember, wherever either voltage or current is negative and the other one is positive, or vice versa, the product of multiplying voltage times current will be negative. In this graphical representation of power, wherever power is negative, I've highlighted it in red so you can see just how much of the cycle is negative. The more red it shows, the more inefficient this system becomes. You can see up near the top of the graph, I'm also showing the amount of phase shift as the graph changes. It doesn't matter if current leads voltage or if voltage leads current. The result is the same. So now, let's add an inductor to our circuit. By adding an inductor to our AC circuit, we create a phase shift where the current lags behind the voltage. Later, we'll see how this impacts the active and reactive power. Here's a closer look at how active and reactive power interact in an AC circuit with a resistive and inductive load. But before we get into the animation, I want to point out that this is a simplified teaching tool designed to help us visualize the concepts of active and reactive power. In reality, current, voltage, and power don't behave exactly as depicted here, and their actual flow in a circuit is far more complex than what we can represent visually. The yellow dots in the animation symbolize active power, the power that flows from the source to the load to perform useful work. The red dots, on the other hand, represent reactive power, which oscillates between the inductor and the power source. While this visualization is not perfectly accurate, it highlights the relationship between active and reactive power and how energy dynamics work in circuits with inductive loads. Please keep this in mind as you watch the animation. So again, the yellow dots represent active power while the red dots represent reactive power. Reactive power does not perform any work. It's more like borrowed energy that's temporarily stored in an inductor's magnetic field before being returned to the source. Only the active power, represented by the yellow dots, is performing actual work. Notice how the yellow dots pause during the negative power cycle while the red dots surge back to the power source. This illustrates the phase shift caused by the inductor. The alternating behavior of active and reactive power is a key factor in understanding power factor and circuit efficiency. All right, to better understand the relationship between active and reactive power, let's look at the power triangle. The horizontal leg of the triangle represents active power, which is measured in watts. The vertical leg represents reactive power, measured in VARs, or volt amperes reactive. The hypotenuse represents apparent power, measured in VA, or volt amperes. The angle between the hypotenuse and the active power leg is called the phase angle. The larger this angle, the more reactive power there is in a circuit, and the lower the power factor. And the higher the phase angle, the more energy losses you'll have in a circuit. Let's do some quick calculations. In a circuit with 10 kilowatts of active power and 10 kVAR of reactive power, the apparent power is the hypotenuse of the triangle, calculated using the Pythagorean theorem. So you get 14.14 kVA as the apparent power. And the power factor is the cosine of the phase angle, or 10 divided by 14.14, which equals 0.707. So the phase angle here would be 45 degrees, and with a power factor of 0.707, we're wasting about 30% of the energy that the circuit is using. Now let's increase the reactive power to 15 kVAR. The apparent power becomes 18.03 kVA, and the power factor drops to 0.555. This means that the circuit is wasting almost 45% of the power that the energy source is delivering to the circuit, and that is a lot of waste. And that's why power factor is such an important consideration, especially in industrial settings. Besides simply costing the user more money, low power factor increases the current in electrical distribution lines, which leads to higher energy losses and a greater strain on transformers, conductors, and other equipment. To address this, utility companies often charge industrial and commercial customers with low power factors additional fees and penalties. These customers can improve their power factor by installing power factor correction devices, such as capacitors or synchronous condensers, which offset the reactive power in the system. By doing so, they reduce the overall current flow, lower energy losses, and they avoid costly penalties. So how does power factor matter for residential customers? Well, it really generally is not a concern. Most utility companies charge residential customers based on kilowatt hours consumed without factoring in reactive power. While improving the power factor might reduce strain on your home's internal wiring, it usually doesn't lead to noticeable cost savings on your electric bill. So what about these devices that are advertised to improve power factor or lower utility bills for residential customers? Well, they typically don't save you money because utility companies charge residential customers, like I said, just based on kilowatt hours used. So these things might reduce the strain on your electrical system, but they're not going to save you money most of the time. Also, in our homes, we don't have a lot of highly inductive or capacitive loads like industries do, where they've got a lot of pumps and motors and things that cause the power factor to drop significantly. So residential customers typically don't really need to worry about it anyway. In conclusion, understanding power factor and its components, active power, reactive power, and apparent power, can help us design more efficient electrical systems. It's not just about minimizing electrical waste, but also reducing the strain on the power grid and improving overall performance. Thank you so much for watching. I hope you found this helpful, and I sure would appreciate a thumbs up. And if you enjoy learning things like this, I sure would appreciate you subscribing to my channel because I do try to make informative educational videos quite regularly. Thanks again. Have a wonderful day. Take care.